Let's solve LeetCode 853 car fleet. There are n cars at given miles away from the starting mile 0 traveling to reach the mile target. You're given two integer arrays, position and speed, both of length n, where position at I is the starting mile of the ith car and speed at I is the speed of the ith car in miles per hour. A car cannot pass another car, but it can catch up and then travel next to it at the speed of the slower car. A car fleet is a single car or a group of cars driving next to each other. The speed of the car fleet is the minimum speed of any car in the fleet. And if a car catches up to a car fleet at the mile target, it will still be considered as part of the car fleet. We want to return the number of car fleets that will arrive at the destination. So what does this mean? Well, we are given two arrays, position and speed, which have 5 elements here, but essentially they can have n elements, both of them n elements. And then a target is given to us of 12, that hey, if this is the position given and this is the speed they're traveling at, this is the target. For example, if they are at 10, let's say the unit is kilometers, there's no unit specified, but let's say for easier understanding it's kilometers. So you have 10 kilometers plus 2 kilometer per hour, which will help us reach 12, the target. The same goes for this. 8 plus 4 will give us 12. But for 0, we'll have to increment it one by one. So at R1, we will be at 1 kilometer position. At R2, we'll be at 2 kilometer. At R3, 3 kilometer. At R4, 4 kilometer, and so on. So after 12 hours, we'll reach the target. So essentially what we want to return is 3. Why? That's because the cars starting at 10 and 8, speed 4 and speed 2 become a fleet. A fleet is essentially one car or multiple cars meeting each other at the target and at the same time. So what happens is that at R1, you are traveling at 10 and speed is 2. At 8, the speed is 4. So both of them reach 12 at a similar time. So the fleet forms at target. So one fleet is created here. Okay. So 10 and 8 are out of the equation. Then we have 0, 5, 3. The car starting at 0, speed 1 does not catch up to any other car. So it is a fleet by itself. Okay, because after 12 hours will this car reach? It's the last car. It will take some time. It will come on later. Then the third fleet that we have is the car starting at 5. So this position and 3. These both become a fleet. How? They're not even reaching the same time, right? They are. So when you have 5 plus 1, 6, and then you have 3 plus 3, 6, you essentially have a car. Like the two cars are similarly going on. So let me draw it out for you. Let's say this is the number line for us where each car is going. All right. I'm just going to draw out the 5 and 3 because it's a very important thing. And by the way, we are told that the entire thing that we have over here is going to be, one way. So, and cars cannot pass each other. So that's good. So what we have is, let's say, a car which is at position 3. So here we have a car at position 3. Just consider this as a car, all right? And then you have another car which is at position 5. Okay? So let's say this is 3 and then another car at position 5. So there we go. Cool. Now this car, the 3 car, is traveling at, what was it? 3 kilometer per hour? Yep. So it's traveling at 3 kilometer per hour. And this thing, 5, is traveling at 1 kilometer per hour. Correct? So what happens is that in the next hour, this car and this car will be at 6, right? Because 5 plus 1 is 6 and 3 plus 3 is 6. So both of these cars will be at the same position. And it's given to us that, hey, if a car catches up to a car, not this one, sorry. It was given that a car cannot pass another car. So this 3, in the very first try, in the very first hour, it is at 6 and this is at 6. But then in the next hour, you might think that this car, the 3 position car will go to 9, because after 6 it will add 3 again, and this 6 car will stay at 7 because it will only add 1 because it's going at 1 kilometer per hour. But that's not right. The reason it's not right is because here we are given that a car cannot pass another car, but it can catch up and then travel next to it at the speed of the slower car. So as soon as both of them reach 6, this car will slow down. After slowing down, this car will travel at the same speed as the forward car because it is driving at a slower speed. Cool? You can think of it as a car that is basically running on one lane. Okay? If they're driving on one lane and you're in a country where, rules and laws are respected, what will happen is that both of the car will basically keep driving like this, and the car that was behind will only follow this car. It cannot go forward, and this car speed will become this car's speed. So it will drop down to 1 kilometer per hour. So having understood that, so once they reach 6, they will travel together at 1 kilometer per hour and will reach 12 together. Cool? So how do we find out how to solve this thing? Well, here's the thing. We are given the position, we are given the speed, and we know that whatever car takes the same amount of time, they'll reach at the same place. Correct? For example, let's take the example of 10 and 8 positions. So let's say we had 10. All right, let me have 10 and 8. The target was 12. This is driving at 2 km per hour. This is driving at 4 km per hour. How do I find the time it will take to reach the final destination for this car and the time it will take for this car to reach the destination? To do that, I can just do 12, which is my target, minus 10, which is the initial position I'm in, divided by the speed I'm traveling at, because I'm essentially following the formula of speed is equal to distance upon time. And we know time is equal to distance upon speed. To find out the distance, we can just do, hey, what is the final position and what is the initial position, right? So this is essentially what we're doing. And this will give us the answer of 1. So this will reach at time equals 1. And what about this? We can do the same thing, 12 minus 8 divided by 4, which will give us 1 again. So this is also reaching the same time. So that means they are in the fleet. For 1, what will happen? So initial speed was 0 for this guy. So initial speed is 0, and then it's traveling at 1 km per hour. So what will happen is 12 minus 0 divided by 1. So it's going to take 12 hours. No other car is going to reach at 12. Then we have 5 and 3. Here's where it's going to get tricky and our logic will have to change. Because 12 minus 3 divided by, let's say it's traveling at 3, right? So here it will become 9 divided by 3, which is equal to 3. So this guy, the guy we have over here, is going to take 3 hours. And what about the guy who's driving at 5? So it's going to be 12 minus 5 divided by what's he driving at? 1 km per hour. So we will have 12 minus 5 divided by 1, which is 7. So it's going to take 7 for this and it's going to take 3 for this. But we know that no, they're going to be one fleet. They're not two different fleets. So what is the problem in our approach? The problem in our approach is that we've not taken into account things like following up on a car. So what we're doing is independently calculating how much time this car will take. Hadn't there been another car in front of it? We've not considered that a car is ahead of the position 3 car, right? So we also need to take into consideration that. And once we take that, we will find out that these two cars are at the same thing. So how do we take it into consideration? Like, what is the trick here? Well, the trick is something very similar to what we had. So the formula that we use, speed is equal to distance upon time, or time Let me just write it down. Speed is equal to distance upon time, which gives us time is equal to distance upon speed. So this is the major formula that we'll be using. Okay. So that gives us a very good idea. Okay. That is a thing to keep in mind. Now, how do we move forward? I like to draw out the number line again. And on that number line, this is the position number line. So one car is starting at 0. Another car is starting at 3. Then another car at 5, then another car at 8, and then 10. So we have 8 and then 10. Cool. So what have I done here? I've laid out all of the cars in an ascending order according to the number line, because in the real world, that's how the cars are moving. If you're in one lane, the guy who's at 0 is going to be the most behind. The car who's at 3 is going to be second most behind. And you can think of it so on. So, right? So, what is my point over here? Well, the very first thing that we'll have to do is sort the cars in descending order, not ascending order, because the car who's over here will get more priority than the car over here. Okay, we'll get to that afterwards. But now, how do I check that 8 and 10 are going to reach at the same spot? Well, we know they're going to reach at the same spot because they are equal. But what if they're not equal, like 3 and 5? How do I check that? Well, the very first thing I'm going to do is calculate the final time it will take for each one. So here the time is 1, here the time is 1, here the time is 7, and here the time is, I believe, 3. And here the time is 12. Are we noticing any pattern? This fleet is all by itself. This fleet is by itself. And this is by itself. So are we noticing anything here? One thing is that if the previous time is equal to the new time, or let's say the current time, let me just say new. So the previous is equal to new. That means the car who's further ahead is equal to the car that's behind if their times are equal. And this time means the time taken to reach the final destination. If they are equal, that means that we have one fleet. If the time of the previous car is less than the time taken for the new car, or let's say the ahead car, then it's one fleet. And if you can notice here, what we have is the car which is at previous, when it's compared with the next car that is ahead of it, it is greater than the next car. So essentially what we're trying to check is that if you have a car over here at 8, let's say this is at I minus 1 and this is at I. So if they're equal, or if they're less than, okay. So if it is less than or equal to, in that case, we are going to have a fleet because we have proven this. For example, if you look at 5 and 8, okay, the time here is 7 and 1. 7 is greater than 1. That's why they're not in the same fleet. But in this case, 3 is greater than 7. Or sorry, 3 is smaller than 7 in that, and that's the reason why they are in one fleet. Cool? So that's the thing we want to do, but there's another thing, and we'll take another solution or another problem to figure this out. And let's try to take 0 to 4. Okay. So we have something like this at 0, 2, and then 4. The final position here is 100. That's a long way to come. 4 is driving at 1 kilometer per hour. So 4 is driving at 1, and 2 is driving at 2, and 0 is driving at 4. When are they going to reach? Well, here's the thing. We can just use the previous formula that we have. So let's go ahead and calculate the time that it's going to take. So 100 minus 4 divided by 1, which is equal to 96. Then we have, or is it 96? Let's see. We have 100 minus 4 divided by 1, right? I believe so. So yeah, it's going to take 96. Then we have 100 minus 2, which is 98. And 98 divided by 2 is going to equal 49. And then we have this, which is 100 minus 0 divided by 4, which is equal to 25. So the car that's the most behind is going to get done very quickly if we just look at it independently. But as we know, we have rules to follow. The car cannot go ahead of this car. So what's going to happen is that we are going to check, hey, if this is I, then I minus 1 is this. Is I minus 1 less than equal to I? Yeah, that's right. 49 is less than equal to 96. If that is the case, then what we want to do is pop this off, because we want to ensure that we only have one in our list. So what we want to do is create a stack here, which will be 96. Okay. And as soon as we get to know that, hey, 49 is less than 96. Yeah, that means 49 will eventually catch up to 96, and then they'll move at the same speed. So what I want to do is, instead of adding 49 here, I can just remove it. There's one car in our fleet, because essentially they both are going to behave like one car fleet. So I can remove that. Then I have this thing, time is equal to 25. And then we compare it with this guy again. So instead of this being treated as I minus 1, this will be treated as I minus 1. And then we compare. 25 is less than equal to 96. Yeah, that's correct. 25 is less than 96. So we are not going to add 25 over here. What we are going to do is keep 96 here, because that is going to be our fleet. Correct? So there's only one car in our fleet. If you want to try it out for this solution as well, you can do it. Let's create a stack here, and then we compare that, hey, the time year and year, 1 is less than equal to 1. Yeah, that's true. We put 10 in, but we don't put 8 here, because 8 and 10 behave as the same fleet. Then we compare 5 with 10. So 7 is compared with 1. Is 7 less than equal to 1? That's not right. So what we're going to do is put 7 here. The reason we'll put 7 in here is the same reason of why we put 10 in here. The reason we put 10 in here is because we want to show that, hey, the car fleet that's ahead of you is at this particular position, okay? And they'll reach at that particular time. What we are interested in is the time, by the way. I'm writing down the positions, but we'll actually be storing time. So we are at time equals 7, okay? We put in 7, and now that's a blocker for any of the previous cars, because if any car wants to travel faster than this car, they can't. So they'll be not added. They'll be added to this like fleet. So this is kind of like a blocker for them. Okay. Then we compare 3 with 7. Then we say that 3 is less than equal to 7. So we are not going to add 3 over here. Okay. Because, well, they're traveling at the same speeds. Because 3 will eventually catch up and then merge with this 5, and then they'll move at the same speed. Then we have time equals 12. 12 is greater than 7. So, well, it's going to travel independently. It's never going to catch up. So yeah, what we're going to do is put in 12 here as well. And that gives us our answer. We have 3 elements in the stack, and that is the number of car fleets. And that's how we are going to do it. So let me go ahead and create a stack which is empty. And then what I want to do is the very first thing. I want to zip up the target and position, not target, sorry. I want to zip up the position and the speed together so that I can easily access both of them. Okay. So what I'm going to do is have zip called here with position and speed within them. So this will essentially give me an array with tuples with position and speed together. And once I get the position and speed together in a tuple, and then what I'll do is just make sure that I do list comprehension, put all of them in one particular array, and let's call this array zipped array. And this zipped array contains the position and the speeds together. This is done so that, when I sort them in the reverse order, both of them are maintained together. It just gets easier for me. If you don't want to do it, it's completely fine, but you'll have to handle a lot more. And then what we want to do is zip.sort, and then we'll do reverse is equal to true, because we want to sort them in descending order, right? Because I was going backwards, if you remember. I wasn't going frontwards, because if I go frontwards, it doesn't give me any value. If 12 is less than 3, well, what do I do with it, right? I can't add 12 because 12 was never the blocker for me. The blocker is the cars that are ahead. That's why we are sorting it. And then what we're going to do is loop over every element in the zipped array. So we have position and speed in zipped. This is the benefit I was talking about. What I've done here is looping through every tuple that we get in zipped and extracting that tuple out, so I get position and speed independently. And then what I want to do is append to the stack. What do I want to append to the stack? I want to calculate the time. So time is equal to the final position, which is the target. We subtract it from position, and then we divide it by speed. This is exactly the formula that I talked about. Time is equal to distance upon speed. And then I append to the stack the time it takes. After that, what am I going to do? Well, once I have the time, I have appended it to the stack. So in the very first case, I've appended 10 to the stack. I don't want to do anything about 10. Actually, I'm not appending 10. I'm appending 1 because time is equal to 1. And then I want to do nothing, because what I want to do next is move to the next element of the array, which is 10. Which is 8. And then I'll calculate the same for 8. I'll append it to this stack, and then I want to pop it off because time here, which is 1, is less than equal to this one. So I want to essentially compare the last element of the stack and the second last element of the stack. And to do that, I can just check that, hey, if the length of the stack was greater than 2, and not just greater than 2, greater than equal to 2, because here when we append to the stack, we are appending another one, and then we are comparing, right? So the length of the stack here is 2. So I have, if length of stack is greater than equal to 2, and what I want to compare is this thing, right? If the stack at -1 is less than equal to stack at -2, correct? Because I want to check that 1 is less than equal to 1, or I want to check 3 is less than equal to 7. So 3 is the thing that will be at stack at -1, and this guy, this 5 or this 7 is going to be the thing that is going to be present at stack at -2. So I'll just check that, hey, if the stack at -1 is less than equal to the stack at -2, that means that we are in a position where the car ahead of us is moving slower than us. So that's going to be a bottleneck for us. So let's just pop off this element, because that element that we are going to have is ultimately going to converge to become as fast as this guy, and we'll reach at the same time. Cool. So again, if we have, let's say, the very first car would reach in time 1, the second set of cars would reach at 7, then what we have is the guy who's ready to reach in 3, but the guy ahead of it is slowing it down, making sure that this guy, the guy who can reach in 3, will reach in 7. So because of that guy, the guy driving slowly, we're going to reach slowly. So that is basically the entire solution. So what we can do is return the length of the stack, because we know at the end, the length of the stack is going to be the number of car fleets. So let's run it and see if that works out. And it doesn't. It says invalid syntax, that for p, s in zip is not allowed. Oh yeah, the reason for that is I've not created a tuple p, s, right? For every element in the zip position speed, I want to have a tuple here. Cool. Let's run it now. And it works out. Let's submit it. And that works out as well. The time complexity of this is going to be O of n log n, because we are sorting the array and then we are also looping through the entire array. So it's essentially O of n log n plus n. But yeah, essentially the time complexity will become O of n log n, and the space complexity for this is O of n, because we are using this zipped array. And I also think that behind the scenes sorting also takes O of n memory. So yeah.